Thank you so much for letting me speak, and thank you so much for letting us have this program. Interesting as it's going to be given all the situation, but it will be fun as always. So the program that we are planning to run with Albert Atserias, Sam Bass, Vijay Ganesh, and Jakob Nordstrom is Satisfiability. Satisfiability theory, practice, and beyond. And I just noticed that we in Canada call it winter, but you call it spring. Oh yeah. So satisfiability is very kind of general problem. You have a bunch of constraints, say Boolean constraints, and you're trying to find out whether it's possible to satisfy them simultaneously. You write down the list of constraints, make it into a formula, and ask if there is a satisfying assignment for this formula. And this problem or significance of this problem is celebrating 50 years this year, because 50 years ago, Steve Cook's famous paper kind of proving the satisfiability is NP-complete and introducing the notion of NP-completeness. Well, he didn't call it NP-completeness. That was a couple years after, with Karp showing that all sorts of things are reducible to satisfiability. And from the theory point of view, this is considered to be an ultimate hard NP-hard problem. We've conjectured that we cannot beat brute force search even by a little bit. People have shown that all sorts of restrictions of this problem, like a linear number of constraints, are still hard. It's believed to be hard on average, and we could show that for some classes of algorithms, it is indeed hard on average. So it's an ultimate NP-hard problem, and yet, from the practice point of view, as practitioners tell us, it's an ultimate easy problem, because a lot of time in industry, when there is a constraint satisfaction problem, the way to solve it is, well, let's code it up as a formula and unleash a set solver on it, and miraculously, it usually works. So let me just mention a couple of examples. For example, when they run FCC reverse auction to buy broadband from TV companies and sell it to mobile companies, I think it was in 2015, they actually used the set solver as an underlying engine in order to figure out to whom they can make lower offers. And interestingly enough, there, the solver running time directly translated into money, because if solver timed out, they would decide that there is no solution and they have to pay whoever's selling it, whatever they decided to pay them. So set solvers have also been heavily used in hardware and software verification, air traffic control. I think in London, they use set solvers to optimize the switches on the railway networks, all sorts of use. And it also had been used to solve some mathematical problem. For example, there was a result a couple of years ago by some people who will be at the program showing that it's impossible to color integers so that all the Pythagorean triples are monochromatic, starting from some pretty big numbers, 7,000 something. And they actually had the proof of impossibility, which was 200 terabytes. Yeah. So the big question is, why does it work? And that's what this program is intended to look at. We're bringing together practitioners, we're bringing together theoreticians from several different areas, and we are going to try to understand why this theoretically hard problem is easy in practice and how to leverage it to make solving everyday problems better. and we'll be happy to run in parallel with TFCS program, which will also bring the theory and practice together, and Moshe will talk about it next.